Hello guys, my name is Aniruddha Kavade. I have done a project called Design of Altera Neos 2 Instruction Subset and its architecture under the supervision of Dr. Chang Chu. So let me first talk about Neos 2. It's a Altera's proprietary software processor basically designed for FPGA. Why I have chosen this processor? Well, it's highly customizable and simple to understand. Tools that I've used are Quartus 2 and Verilog. This is the instruction subset that I have implemented. You can find more about these instruction set on the Altera's website. I have mentioned the link of the same below in the description. This is the design. It's a 5-stage processor. First stage is instruction fetch, second is instruction decode, third is instruction execute, fourth is memory access, and final stage is write back. At the initial reset, all register values will be 0 and there won't be any instruction in any of the stage. First instruction will be ORHI, R2, R0, R0. It will consist of it will be passed on to the next stage at the next clock edge. Now in the next clock's edge, PC increments and IR will have a second instruction, ORI R2, R220. Because of pipelining, first instruction will go to the next stage, but second instruction will try to acquire a value which has not yet been returned that's specific to register. This phenomena is called data hazard. That's why we will need to introduce a phenomena called stalling. Now, stalling prevents execution of new instruction till the write back of previous instruction has occurred. This is very important to prevent data hazards. So in the next clock cycle, because of pipelining, same instruction will be passed on to the next stage. Again in the next clock cycle, same thing will happen. In this cycle, write back stage and fetch stage will have same instructions and hence they will be active. Now next instruction is passed on to the first stage. In the next clock cycle, PC increment and instruction move ahead. Now again, to avoid data hazard, stalling will happen. As you can see over here, register R2 is 0. This is because of ORHI R2 R0 instruction. So now in this stage, the problem of data hazard will again occur. So stalling must have to be done. The same instruction will be passed on to the next stage, but the other stage will remain active although the first 4 stages are inactive. So execution of ORI R2 R220 will occur and register R2 will get value 20. Now new instruction is accepted and old instructions are passed on to the next stages. Again, because of data hazard, stalling is done. So and instructions are passed on to the next stages till the write back happens. Now in this stage, new value is put on in the register file, and we will get value 60 in the register R5. The previous instruction ORI will be passed on to the next stage till the write back stage. Instruction at the write back stage matches with that of the fetch stage. Now in this stage, ORI will be passed on to the decode stage, and new instruction LDW R4 R0 R4 is accepted. There is again similarity in the registered use in both the stages, which is R4. So data hazard will happen and stalling must be done. Now the same instruction ORI R4 R408 will be passed on to the next stages till the write back stage occurs, and the instruction in the write back stage and the fetch stage is same, which happens over here in this clock cycle. Write back value 08 will be fed to register, and the new instruction add R5 R0 will be accepted. Now as you can see, there is no issue of data hazard, so all stages will be active, and instruction add R5 R0 will be passed on to the next stage, and new instruction LDW R60 R2 will be accepted at the same time. Now there is no data hazard, so all instructions will be passed on to the next stages, and new instruction LDW R70 R3 will be accepted. Now at this stage, because of write back of LDW R4 R0 R4, value 6 is stored in the register file, and the new instruction mul R8 R6 R7 is accepted. But as you can see, the highlighted registers R7 are common in both the stages, so stalling must be done. The instructions are passed on to the next stages, but although previous three stages are inactive, the next stages will remain active as there is no problem of data hazard. So execution of add R5 R0 will store value 5 in the register file. In the next stage, instruction LDW R60 R2 will be executed, and value 2 will be stored in the register file. Now new instruction accepted by the fetch stage add R5 R8 has same register R8 as that of decode stage, so stalling must be done. This operation will happen again, stalling will happen again till the time when write back register has same instruction as that of fetch stage, which will happen at this clock edge, and we will have value 10 in the register file, and previous instructions will be passed on to the later stages. Now again at this particular clock edge, fetch and decode will have a common register R4 and stalling must be done. This will happen in all the stages, in the latter stages, and execution of write back instruction will increment or decrement value at the register file. Now let me move ahead to the last instruction, BR18, which will change the value at the register file. This is the last instruction, and at this stage you can see register file is been updated to these values. Thank you.